Okay, Jam, remember last week we talked all about the chemistry of film and how science turns into pictures?
Yes, I remember all about it.
And I left you on a little teaser about color film because it's totally different
Mm-hmm.
and also Polaroids.
Yes. Mm-hmm.
So today we're going to get into those.
Yes.
So are you ready to learn about how the pictures we take turn into the pictures we see?
I'm so ready. I'm so excited. Like several of us and listeners who have been asking this question
For a very long time.
Yeah, I'm very, very ready.
Yay. Okay. So if this is the first, this is the second of a 2-part episode.
Correct.
So
right.
if this is the first one you're hearing, you really need to go back to the first one because I'm pretending like you've definitely heard that.
Right.
Which is not usually what I do. I usually try to say like, oh, if you want more information, go to this. But here's a quick overview. Not on this one.
Okay.
So before we get into the episode, I want to strongly encourage you to go back and listen to that one because I'm just going to be rolling straight through from there.
It should be easy to find, right? It's like probably we had our Q&R.
Yeah.
And then the
It's
film
like 2
one before
episodes
that.
back. Yeah.
So yeah, you can find it.
Yeah, you can. I have confidence.
Yeah.
All right, let's get started.
All right.
Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast that helps you understand the chemistry of your everyday life.
And you know what occurred to me is I said, let's get started, but I should have said, let's keep going because we've already started this once.
Right.
Okay, so we talked about black and white photography.
Mm-hmm.
And I was like, color is hard. Okay.
Right.
So this whole episode is going to be devoted to color theory.
Okay.
Okay. So there are 3 basic colors that we as humans can see, that we can use to perceive color. And that is red, green, and blue.
Okay.
Now, tell me what you know about that, because you're a film person, so you might have already known that. But other people are like, no, the 3 primary colors are red, yellow, blue.
I did know that. One of the things I'm confused about a little that, I don't know if this came up in your stuff, but is that people end up saying, I guess this is more for digital stuff, but I wasn't sure if this applied to our eyes as well, that it's a little bit more accurate for some reason, on all things digital, all our phones, our printers, TVs, everything, is it doesn't do that. It does yellow, cyan, and magenta.
Yep.
And so what I'm curious about is that how our eyes are too? Or is that specifically sort of relegated to...
Okay, so let me tell you how yellow, cyan, and magenta get there. Okay, so if you have red, green, and blue, and maybe we could do a nice like color something that would show this on the screen right here. If you can get a Commons free one.
Okay.
Or you can look up additive primary colors. But the additive primary colors are red, green, and blue.
Right. And there are a lot of LED TVs that use that instead of the CMY.
Lots of CMY is cyan, magenta, yellow. But a lot of TVs use, that's the color we use, is this additive theory where if you add red, green, and blue, you get white.
Right.
And then if you just mix 2 of them, like for example, if you just mix red and blue, you get magenta.
Right.
And if you mix green and blue, you get cyan. And if you mix red and green, you get yellow.
Yeah.
And so those colors that overlapping, the yellow, cyan, and magenta, if you do the opposite of adding 2 colors together or 3 to get white light, if you start with white light and you take things out of it, for example, if you have white light and you take blue out, that would leave behind a yellow and red. That would leave behind a red and a green, which combine to make yellow. So that is known as the subtractive colors.
I see.
So if you're thinking of starting with individual lights and overlapping them on one another, then you can do additive colors where we add these 2 together and see these things. But if you're thinking of starting with white light and taking things away from it, then it makes more sense to say like, okay, if we're taking away blue, then we'll get yellow over here. Or if we take away red, then we're going to leave blue and green, and that makes cyan.
Right.
Sort of thing.
This is also weird to me too, because having done like a lot of painting in high school and stuff, through middle school and high school, it is the classic way we learn it, where it is like, if you have paints, if you have a yellow, you actually use the regular primary colors that we grow up talking about. And you are going to mix red and blue to get purple. You're going to mix red and yellow to get orange. You're going to mix yellow and blue to get green.
Yeah.
And you can play with those ratios a bit to make different sort of more nuanced colors. It's just so weird that light is not the same as paint.
Yeah.
Like, what's going on with that?
I'll say that I think light being not the same as paint, that's like a harder thing to say. But I will say those primary colors, red, yellow, blue, are very close to yellow, cyan, and magenta. And I honestly wonder if we use those primary colors because it's just like the actual ones from light tweaked in a way that's easier for kids to learn in primary school. So that's what I think. But it is a little confusing. And one thing I saw, and I don't know how true this is like, if you're talking about light and the way light adds up and our brain perceives it, that's different than pigments on paper. And so like if you combine all three of the colors for light, you get white. But if you combine those three subtractive colors, cyan, yellow, and magenta, you get black. And so I wonder if it's going from light to pigment that makes it different.
Interesting.
Because in the pigment, we're seeing the reflection of the light, like what's being absorbed and what's being reflected into our eyes. So it's sort of like the opposite of what we're seeing for light.
Yeah.
Okay, so I'm glad that we're having this conversation because this is the basic of what we're going to talk about today for how film works. Okay, so the three basic colors, blue, red, and green, are the things that what did I say? Blue, red, and green. Yeah. Are what we can see with our eyes because we have photoreceptors in our eyes. Photo comes from photon, which is packets of light. And so these photoreceptors can respond to light. And we talked about rods before.
Right.
When we talked about if carrots can help you see better. But we also have cones. And the cones are the three ones that allow us to perceive those colors, blue, red, and green.
Okay.
And when all of them are stimulated equally, we perceive that as white light. But like you said, if we do them in varying combinations, we can get all the potential colors. And those primary colors of light do, when you add them together, give you these different colors in different amounts. And like we said, if you combine just two, you get those yellow, cyan, and magenta.
Yeah.
And that is, like you said, some of the theory. There's a lot more chemistry behind color television, which I found out while I was researching this. And I was like, should we do a TV episode?
Maybe so. Dude, that'd be cool.
So. And then I was like, not today's problem.
Yeah.
So, but that is the idea behind the color of TV is they only use those three colors.
Right.
And those three colors are enough to give us all the colors that we see on TVs, on photo screen, like on our phone screen, things like that you can see. Okay, so that's the additive theory where we can add these together to get the things we want. But there's also these subtractive colors, and they're going to come back up.
Okay.
In color photography, because color photography, we can't just lay layers of color on top of each other to get what we want, right? We are, the way that film photography works is we are opening a shutter, and that shutter is putting light into this contained area, and then we develop that into film or into photos. So it's like you can't just shine light. It's like where you have to convert it somehow to pigment on a paper.
Right.
Okay, so here's how color photography works. Is it starts with film, just like the last time, and it's coated in, now this time, 3 layers.
Okay.
And each of those layers are what we would call dye-sensitized silver halides. So we talked about silver halides and the role they played last time, how they absorb light. It's converted to silver is basically converted, silver ions are basically converted to silver metal.
Okay.
And that's how we know like that, where that reaction happened. Then when we put it in the developer, it sort of makes more silver metal form and it's easier to see, we talked about that. Okay. So in color photography, we now have these silver halides that have what we call dye sensitized, like things attached to them, basically. So they're dye sensitized silver halides, which means that instead of the silver halides directly absorbing the light, now these dyes, which are sensitive to specific colors, they'll absorb energy and then transfer it to the silver halide, and then the reaction will happen.
Okay.
So just shining light on it isn't enough. It has to be light in these specific colors.
Right.
And they have the 3 colors. Each layer is dye sensitized for blue, green, and red, just like our eyes.
Okay.
And that's not all that's in them. They also each have what we call a coupler, which I think the best way to think of this is like a pre-dye. So each layer has its silver and its photosensitizer, and it has what that layer needs to later react with developer to become a dye.
Okay.
So that it can have the colors that we need.
Okay.
So that's what each one has. Okay, so let me look at my notes because I wanted to be very sure not to skip anything here. Okay, so the reaction happens the same way as it does. The light will shine, but only specific light will trigger a reaction on each layer. And then the silver metal is formed, and we have that silver metal that's in the latent image, and then that will be amplified. And then we have this coupler that will react when we put it in the developer. So we're not just maximizing the effect of silver, but we're also selectively choosing which light it reacts with, and then we will ultimately give that a color to go with it. Okay. The trick is the color of the dye is the complementary color of what's absorbed.
Okay.
So for example, we said earlier that if you have white light and you take away green, that leaves behind red and blue light.
Right.
That makes magenta.
Right.
So the layer of film that is sensitive to green light is paired with a coupler that's magenta.
Okay.
And we'll talk about why that happens in a minute.
Okay.
But the same thing is true for the level that's sensitized to red light. The dye that it's coupled with is cyan.
Okay.
And the layer that is sensitized to blue light is the dye that's on that one is yellow.
Okay.
Okay. So, and remember, if you add all 3 of those together, you get black.
Right.
Those 3 pigments go together to give black.
Right.
Okay. So what we do in film is try to make negatives. So instead of doing what we do with our TVs where we can add everything together, in film, we're subtracting color.
Right.
And so I thought it would be easiest for us to talk about this in a picture, like in your mind, picture in your mind a green plant. And I actually took a picture of a green plant in a black pot. And I thought maybe you could put this up on the screen. I'll put my hand here so you'll know where it will go. So here's just a picture of me holding people at home who aren't watching on YouTube, you can still picture this. It's like a dark gray pot and a green plant and a white background.
Right.
Okay. So if we were taking a picture of this with a film camera and we opened up the light, let's say the light first hits the blue layer. So anything on this image that has blue light will react on that blue layer and turn that silver ion into silver metal.
Right. And so it's probably pretty sensitive to it in the sense that, like, even in things that we cannot tell have blue in it, like that dark gray, for instance, probably does. And obviously the green does. Yeah. It's like it's in there. And so whether or not it's obvious to our eyes, it is there and in that like range of light, the way that, So it's not perfect. Right. But if you pretended like this was pure 100% green and there was no blue in the plant at all, then that layer, that area where the green plant is, it would not react at all with a blue layer. Right. But where there's white,
it would react with the blue layer.
Right, because there is some in there as well as everything
because
else.
white, red, and green make white. What did I say? White, red, and green? Blue, red, and green make white.
Yeah.
So if we were like pretending it was perfect, but you're right, it doesn't give the exact.
But what was helpful about that is thinking about, okay, we can't really pick up on it necessarily.
Yes.
But when the light's just coming and all sorts and amounts that we can tell and amounts that we can't really, but it's there. And so if there's just at least some, that layer's going to know.
And that's how we get all the shades of green and stuff. Yeah, exactly.
Right. It's helpful to know that it's like, it's sensitive in a way that we are not.
Yes.
Or whatever. Yeah. Or we are, but we aren't consciously not.
Yeah. If there is any blue light, it would react.
Okay.
And then same thing with the red layer, the white area in this picture, the white background in my green plant picture, that would definitely react with the red. But the plant, again, probably not.
Okay.
And again, the black on here is probably not.
Yeah. Okay.
And then we get to the green layer, and all of the white reacts with in the green layer, and so does all of the green, because now green is definitely there. So that's kind of interesting because the white part has all three of these layers reacting, but the green part is mostly just in that last green layer.
Yeah. Okay.
Okay. So each one of these, that's how the reaction takes place.
Okay.
So that then you have to think about like, okay, all right, so each one of these reacted. And so what we would get then for the white area is there's been a reaction in every level. For the green one, the only reaction that we've had is in green, which means red and blue are still largely left untouched. And so if we were shining the light of that together, the red and blue would combine to make it magenta.
Okay.
But in color film, we're not shining the light on it anymore. We shine the light to have the initial reaction. So to mimic that sort of like, oh, this is what's left after these react, that's why the developer will develop a complementary color dye. So anywhere there was green, we get instead magenta.
Right.
Okay, and I actually went to the trouble of turning my plant picture into a negative for you.
Nice.
So you can see the green plant is like it's not exactly a true 100% magenta because but it is like a pinky purple color.
Yeah.
And the dark gray pot is like looking white.
Yes.
For sure. And so is my black watch. And all the white area around is looking pretty dark.
Yes.
Because all of the white light was used for the most part. Okay, so now imagine that in your mind. And instead of thinking of it as like a solid color, if you can picture that as a transparency, like this is a see-through thing on a piece of plastic, and we shine white light through it. If you shine white light through magenta, the magenta will filter out everything but the green.
I see. Okay.
And so you shine that through the negative onto the photographic paper, and what you get then is the only light that's able to come through is the light that you had absorbed previously. So you basically made a filter that will filter out all the light that you don't want by making the negative image.
So, and the photo paper, not trying to get ahead, photo paper is sensitive in the way that makes more sense to us, which is it's looking for the color green. And because green will not be filtered out, it will come through.
Yes.
Green will look green on the photo paper.
Yes, exactly.
Okay, got it. I was thinking for a second, I was about to get confused, and then you fixed it for me.
Okay, good.
Because I was like, I know that with like slide film, like those like carousel kind of slide things, those have to be positives.
Yes.
Because you're not shining on the photo paper, you're shining them onto a wall to look at them with your friends or whatever. So
and the difference is in how they're developed.
Right.
So they're not coupled with an inverted dye. They're coupled with the matching color dye, and then they project like overlays.
Right.
Which is a foray into another. I did read about how the chemistry of those too.
Yeah.
So the key thing is in the development, whether you get the negatives or the positives.
So basically you are doing literally 2 developments here.
Yes.
Like there's 2 different stages of chemical coatings that are sensitive to a certain type of light and will react.
Yeah.
And because there's those 2 stages, okay. Yep.
And I decided not to go in depth on the photo paper because I feel like actually the color part of this is confusing enough that I think that's enough of a chemistry lesson on its own, that we're thinking about like, okay, so light, the electromagnetic spectrum, we're shining that onto this thing. It's causing a chemical reaction. And then we as humans are like, okay, now how can we turn this chemical reaction into an image? And it does require that converting from what the color theory of light to the color theory of like paint, paper, ink, which is that subtractive one, which is like, oh, we're adding all this together and it makes black. What's up with that? You know?
Yeah.
So we almost do have to convert that way.
Yeah.
So that then we have something we can shine the light through to get back to where we want to go.
Right. And that makes sense too why printers use CMYK, not RGB. It's like they're adding it on top of white paper.
Yep.
So it's like, it is like, okay, we have a different problem here.
Yeah.
That we're having to, we have to go a different route to recreate the same image.
Exactly.
Yeah. Okay. Wow.
And if I think too hard about it, sometimes I get myself back confused. So it is because you're like, why do I combine these and they make white light and I combine these and it makes black? But it is like, okay, well, you're starting with nothing and you're combining these light colors together. Whereas over here, you're starting with white and you're taking things away so that it will. So we're doing a different thing here.
Yeah. You already corrected me earlier, but just so that people don't jump in the comments hardcore, the thing I said at the beginning about CMY is only true in the situations that Melissa said. And the thing about RGB, red, green, blue, is true in most of the other scenarios. So I think I said TVs and phones and said CMY earlier.
Oh, it's like in printers.
Yeah. Because in things like printing any physical media that does not have a light behind it.
Yes.
Right. So okay.
But phones, TVs, anything that is shining the light, it gets to do the adding together.
Yeah.
Which to me is easier to imagine. For some reason, I can imagine like transparencies where I can transparencies is dating me. But when Jam and I were young, there's actually one professor at UNT who like saves one of these off to the side so he can still use it. But when Jam and I were young, our professors had these and teachers had these clear pieces of plastic that had color on them, and you shone light through them, and that would get projected up onto the board. So like now we just use document cameras. Yeah. And so, but because of that, I could very easily imagine like putting a red, a yellow, and a green on there, and then making all these colors. But taking colors away is like harder for me. I don't know. Anyway. Yeah,
that's interesting.
So it is a little. It's a kind of a hard thing to cover. But so essentially we have this negative image where, the plant, instead of being green, is the absence of green, which leaves behind red and blue, which makes it like this pinky purple color, this magenta. And something that is a white surrounding, because all of those were activated, it looks black. But if you shine light through a black transparency, none of it's getting absorbed because black is the absence of color. If you're shining it through a black filter, all of that can go through. And so it will look white on the photo paper. And then the things that are white in this transparency, the filter, all the light is being absorbed. You're blocking everything that's that color. And so it looks black when we get to the photo paper.
Okay.
And so that's how it sort of becomes a picture.
I see.
And so that is essentially the principle behind color photography, is that there are these layers of silver that act exactly the same way, but instead of letting all the light hit them, the only light energy that they can absorb is regulated by these these sensitizers that they're paired with. It's like something that will only absorb in the only absorb in the blue, only absorb in the green, only absorb in the red.
So on the negative, just make sure I'm getting it correct.
Mm-hmm.
On the negative, like in your plant picture, for instance, the wall is white.
Mm-hmm.
In real life, in the negative, it is black.
Yep.
So on a negative, this is printed onto like the plastic, whatever you would call it.
The film,
like celluloid stuff.
Mm-hmm.
The black part would actually be transparent. Is that what you're saying?
The black part, you could shine a white light through it and it wouldn't filter that light out.
Right. Okay.
So you filter out, essentially, it acts as a filter that will filter the color you see.
I see.
So you'd filter the magenta, leaving behind only green.
Got it. Okay.
Or you'd filter out the white, leaving behind nothing, no light. Or the black part could not filter effectively because there's not black in light.
Yeah.
And so all the white light gets to go through.
Okay.
So, and just because it's black doesn't mean it's like solid black. It's like a black color filter, I guess.
Yeah. Okay.
So you can think of it kind of like that.
Yeah.
And if we'll have the picture up so you can kind of see what it looks like on here, but also you can look up. It's really interesting to see like color negatives get converted into like what the conversion looks like. You can just Google it and see.
Yeah. Interesting.
And now you know why negatives look like that.
Yeah, on my like film scanner, because it can scan like slides, and it can scan negatives. You obviously have to tell it like which thing you're scanning.
Yeah.
So that it will just do the conversion for you, but it won't if it doesn't know. And so it'll just be like, if you don't turn that on and you scan your negative, you'll just end up with a high resolution negative, like weird looking photo.
I do remember when I was a kid, like holding them up and being like, I look like a scary monster in this negative.
Yeah.
Like my teeth are black.
Yeah,
and
my like the pupils of my eyes are like white and they like, look weird, like a monster or something. Yeah.
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 And okay, so do you want to try to say that back to me? And then as a little treat, I'll give you the basic idea behind Polaroids.
Yes. Okay. So, in our color film camera, just like the black and white film camera we talked about last time, we, open the shutter very briefly and close it again on whatever we're taking a picture of. Say the plant in the pot. And this time our film has 3 layers of coatings. And each layer is looking for it is looking for RGB, right? It's looking for red, green, blue.
Yep.
But so when the first layer, let's go with blue again, or let's go with green because the plant's green.
Okay.
The green layer, when it is hit with the green light, it is I'm forgetting the names of the 2 different molecules you talked about that are like paired together.
Oh, it's called a sensitizer for the silver.
Okay, for
the silver halide that becomes silver metal.
We're still talking halide here, silver halide, but it's sensitive to a certain color, but it will, so that'll like activate it basically, right?
Yeah.
But it'll actually sort of trigger the presence of the complement, the other color.
But that happens in the development process.
Right. So right now, all it's done is basically these, see the previous episode, these silver halide molecules have been altered now that they have been in the presence of the kind of light they're sensitive to.
Exactly.
Okay.
And they become silver metal.
They become silver metal, and obviously that varies across the whole image in these like very nuanced ways.
Super nuanced ways, yeah.
And so that happens on every layer. The green of the plant happens on the green layer, red if there's any red, blue if there's any blue, and then if there's white, all 3. Yep. If there's black, none, I guess.
And you can get combinations, like if there's yellow, that would be the green and the red layers react, And And there's like, tons of of course, every variation of color that could possibly exist is as a result of combining these three in different proportions.
Right. And so when we develop them, they end up actually developing their complementary color. So the process of developing this color film ends up with wherever the crystals, wherever the halide has turned into actual silver metal, on each layer, the green layer will turn magenta.
And that is because the dye is packaged with the layer.
Okay, packaged with the layer, but not until we've like introduced the development chemicals does it do what we talked about in the previous episode, except per color.
Yeah,
right?
and it like the dye develops, it reacts with the developer to make the color.
Okay.
It's like a pre-dye, pre-color until you put it in the right film. There are some where the film doesn't have the dye and you have to do it in the developing process, but it is much harder to do that.
I see.
And so the much more popular, much more common color film is one that's sort of like packaged with the dye, with the pre-dye in each layer.
Okay. So does that mean does it have additional like baths, or is it just the one because the pre-dye is already there?
I think if it has a pre-dye already there, then you can just use the main
main bath and then the stopping one.
Yeah. And I think they do actually destroy the silver because, silver blocks light. And so they don't want to do that. So I think there's a step where they destroy the silver and then they do the developer that'll make the dye colors that we want.
Okay.
I don't know exactly the process there. I just know that there's like a developer solution that will trigger the pre-dye to react. They basically react together to make those dyes.
Got it. Okay. So, and then after doing that, we are left with a negative image where everything that we saw in the picture we took is represented by its opposite color so that it can create a filter.
Exactly.
Where only the actual color of light will pass through. So we will shine white light through it and it will hit a magenta colored plant, right? And that would mean the magenta color light will be blocked, but the green can go through.
Yep.
And hit the photo paper, and then we'll get a positive,
exactly,
actually representing what we are expecting. But it has to filter out any light that is not supposed to be there, or let through,
right?
And or let through. And in the case of like white and black, it'd be all or nothing, and then we'll be left with a photo that looks correct.
Exactly.
But we didn't go a lot into that process, but that's more like the subtractive. Is that what you said? Or is that additive?
I think it's additive because the green light shines on.
I see.
And you're well, I guess you're starting with white light, so it could be subtractive. But I think I don't know the chemistry behind the photo paper.
Yeah.
I didn't look into that. I wanted to focus on the film itself.
Yeah.
Okay.
Did I miss anything?
I don't think so.
Man, that's a lot.
Do you have any questions? I feel like we did kind of like the flyer review. I spent hours learning about this. Like normally I don't have to spend this much time, but I think I probably spent cumulative 10 hours on understanding photography and color theory.
Dang.
And I feel like it's distilled into such a small, there's like so much time, and then now we're just a small bite. But do you have any questions?
I had the question about 3 separate baths or not. We talked about that already. With the
I think
pre-dye.
they do sometimes.
Okay.
But no, I don't think. I think they just do the same number of baths.
Okay.
Okay, and then you also wanted to know about Polaroids.
Yes, and all I do know is simply that my understanding is that there are some amount of developmental chemicals in that little pouch at the bottom. of the photo.
Mm-hmm.
That's it.
Okay, so that's true.
Mm-hmm.
I don't know if it's in the pouch at the bottom, but I do know that there are developer chemicals in, like, they're sealed.
Okay.
And when it comes out of your camera, the rollers roll over it and burst the sealed developer pouches.
Okay.
And then they start developing right there.
Okay.
But instead of creating a negative and then shining the light through to make the positive, essentially only certain of the yellow, magenta, and blue, yellow, magenta, and cyan dyes are allowed to come to the surface. And I think we could do a whole separate episode talking about how that happens. But essentially, then they're able to come to the surface in the right amounts. And that is how the Polaroid happens.
Wow.
So it does the same, like, light reacts with silver halide. We get the silver metal. And then there's, like, layers. Same thing. There's layers of, like, the blue sensitive, the red sensitive, the yellow sensitive, and each of your dyes will then be formed. And then they, I think, instead of like, okay, and so now we have a negative, they block that one from rising to the surface.
Interesting.
And so there's, I actually have and we can maybe put this on there. I think we'd have to cite it. There's a really good article called The Chemistry of Color Photography, and it was made by two professors at University of South Florida. I think Gita and Raber, maybe, is how you pronounce their names. And they have a nice visual image where they kind of show, like, this is the what a Polaroid probably looks like, where you have the clear plastic layer, and then there's like the polymer layer, and then a timing layer, image receiving layer. So I think the timing is like it keeps it blocked until it's time. But there's blue sensitive, green sensitive, and red sensitive, and then there's a opposite color dye developer under each one.
Oh, I see.
And so their dye developer is there in the layers, but then they don't let them all rise to the surface.
I see.
Only the right proportions of the different dyes rise to the surface.
Wow.
To where you can see it at the top.
Wow.
Isn't that crazy?
That is crazy.
It's like so complicated.
Yeah.
But in other ways, it's like, oh, that makes sense.
It makes you way more impressed that people even figured this out.
I know.
It's like one of those things where, you know how you'll hear something. I mean, in my case, I'm not seeing these peer-reviewed articles. I'm seeing like just a regular news article for pedestrians that says something like, scientists are beginning to make progress on blah, blah, blah. And it'll basically be like, oh, they saw this distant star in a telescope and you see it and it's like, okay, it's kind of you're barely able to tell what's happening there.
Yeah.
But it's just kind of like, oh, there's a promise of some future interesting discovery here.
Yeah.
But it's very like, we're doing the best with the tools we have, and it's not impressive to the regular person yet, right? I kind of feel like that would make more sense if we were like that at that place with photos, where they're like, basically, we've just started figuring out how to make a certain chemical like react to certain types of light.
That's the part that
others.
makes the most sense to me, that I'm like, oh yeah, we can adjust conjugation and make this absorb light in this specific wavelength.
Right.
For me, that feels easy.
It seems,
and we've talked about episodes with like that before.
Yeah. It seems like when it comes to the like super specific detail of it, that's what's impressive to me. To say like, oh, we can have this thing glow. Like that's not that crazy. I'm like, oh, it's glowing. It's cool.
Yeah.
But it's like, oh, it's not recreating an image, you know?
Yeah.
But the idea of like, oh, we not only did we get these coatings to be sensitive to certain types of light.
I know.
We've also gotten it where it's insanely accurate.
I know.
To our eyes, at least. That's where I'm like, how are we already here, and how have we been here for like 80 years?
Yeah.
With color film, at least, right?
It's crazy.
I don't know, man.
I think that a lot about TVs and stuff too.
Yeah.
I'm like, this is wild.
Mm-hmm.
I will say I feel like there is a lot more to Polaroid cameras. I teased it last week, so I kind of wanted to give you the overview of it.
Mm-hmm.
But I do think we could do a whole other episode on like how and why only certain dyes get to diffuse to the top to where we can see them.
Okay.
But it feels like it's beyond the scope of today's, because what are we already at, like 40 minutes?
Yeah.
Yeah. So.
Smart.
But I just wanted to give you a little overview.
Man, I loved that. This is so fascinating.
Isn't it so fascinating? And it was very satisfying to me to be able to like say, okay, this makes a little bit of sense. But sometimes it does feel like I'm just barely grasping on when it comes to color. We've talked about that before. There's so much about color that I'm like, I think I have it.
Yeah. Yeah. And even like, I mean, in the way that our recording schedule worked, you said last week for the film one, but it was like, what, 3 weeks ago?
3 weeks ago, yeah.
So there was part of me that was like, oh man, I do have that in my brain. I have to work a little harder.
That's probably how our listeners feel too.
Yeah.
All right. Well, I think that's everything. Do you want, normally we finish up with a category, but maybe it would be fun to do like, what's your favorite black and white TV show?
Oh, that's cool. Favorite black and white TV show. Okay. How many black and white TV shows have I really watched?
I have mine.
You have one?
Yeah.
Go for it.
I used to watch I Love Lucy with my mom late at night. And, you know, there's like the one of her putting all the chocolate in her mouth in the chocolate factory. That's very famous.
Classic, yeah.
So I loved I Love Lucy. I think that's probably, and we also watched Lone Ranger.
Oh, yeah.
Which now I'm like, that's probably problematic. But
yeah,
I Love Lucy was definitely one that we watched a lot in black and white.
My grandmother liked that. She also liked Andy Griffith. That was in black and white, wasn't it?
I think it was at first, and then it turned into color later, maybe.
Really?
I think, maybe.
All of the like
Andy Griffith I also watched a lot.
All the little snapshots I have in my head of like Barney doing his thing and stuff.
Yeah, black and white. You're
Black
right.
and white.
Let's see.
And then the first like 3 or 4 seasons of Mr. Rogers' Neighborhood are in black and white.
It got color later on. And did you ever watch The Incredible Mr. Limpet? Didn't it start out in black and white and turn?
I don't know if I've ever heard those words before my entire life.
Are you serious? It has the guy. Okay, I think it starts in black and white. The Incredible Mr. Limpet. It has the guy from Barney. It has Barney.
Oh yeah. Don
and
Knotts.
He doesn't like his life, and then he goes down and becomes a fish.
Oh, interesting. Yeah, I never watched that.
So that's him as a fish.
Oh, I see.
I don't really remember much of it. It might start in black and white.
Yeah.
Though. And like it's similar to how Wizard of Oz, you know?
Yes.
But I don't know for sure.
This is also was done in black and white for a few stylistic reasons, but this like really good French movie called La Jetée. Probably be my favorite black and white thing.
Okay.
But it's not a TV show, it's a movie. So
yeah. So is The Incredible Mr. Limpet.
Okay. Yeah, but it's very good. Like holds up. Like the black and white actually is a huge asset, I think. It makes it much more interesting. But I think it might be just because that's all I know it as, but I think it gives it more of a like drama to it.
A vibe.
Yes, definitely.
I also think Pleasantville played on that, where it was like they went back into black and white, and as people like learned how to break out of these specific roles,
they were becoming color.
Yeah.
Yeah.
It's been a very long time since I watched that.
Me too.
So I don't remember what it was like at all. So don't take that as an endorsement of that one. All right, great. Well,
cool.
Thank you so much for asking about this and being patient. I definitely think that we could do a whole other episode about Polaroid, so that's definitely still on my mind. But I think for now, just knowing that like it has everything in there and the little rollers burst them and it does the process in situ, I think is a good place to go. That's
pretty awesome. And thanks for teaching us and doing all those deep dives and spending all those hours trying to understand it and read through it all.
Absolutely.
So that we could learn about it. And you know, we were those of us who were asking about this, we were patient this time, but just be careful because next time, who knows? Like, what if we all band together and like riot, you know?
Listen, it's hard.
I'm just kidding.
It's hard. I'm doing the best I can.
No. This was worth, it's all worth the wait. I mean, what are we going to do?
Good.
Like, how good of an episode would it be if we forced you to like figure it out with limited time, you know?
Yeah.
Could you in the future, this is more of a trivia thing. I've not looked into this, but a very famous sort type of film was Kodachrome by Kodak.
Mm-hmm.
Could you at some point just look into what was distinct about it?
Mm-hmm.
Was there anything more than just a brand name? And did they have anything cool that they were doing with it? Because it was kind of famous. Partly because of the very, very good Paul Simon song called Kodachrome.
Okay.
So that could be part of it. It's like it had a good tune. So maybe that's why it got so famous. But I've wondered with some of the different types of film that aren't just about the like sensitivity, that ISO to the sort of, you know, how bright or dim are you shooting, what environment you're shooting in. When there's like, oh yeah, this is this certain Fujifilm, whatever grade kind of, so to speak. I'm curious, like what they're really doing there.
Yeah.
That could matter or not.
I think one of the papers I read did talk about that.
Nice.
About it being like, there's a whole section on like accuracy of color and like how we get that. So I think in that one paper that I referenced, that was a super useful resource. So I can look back at that and see.
Nice.
And I've added this to my August bonus episode questions.
Heck yeah. Thanks for teaching us. I was starting to go in that direction and then I didn't. Then I changed my direction. If you have a question, thought, idea, follow up to this or about anything else in the world, you can, as long as it's about chemistry at least, you can reach out to us on our website at chemforyourlife.com. That's chemforyourlife.com to share your thoughts, ideas, and questions. If you'd like to help us keep our show going and contribute to cover the cost of making it, you can join our super cool Chem community of patrons on patreon.com/chemforyourlife. There you get some perks, some ways of us saying thank you. You get ad-free feed of the show. You get a bonus episode every month where Melissa and I just hang out and talk about stuff. Recently, we had one where we did a media swap where I watched Aaron Brockovich and Melissa watched Oppenheimer, and we talked about it.
It was really fun.
A lot of fun. And yeah, it's just really cool to get to engage with y'all over there. So we'd love to have you if you can. And most importantly, you keep the show going and you keep it free for everybody. So that's a big win for all of us. So thank you to our community, and thank you for considering joining over there. You can also help us by buying some of this sweet merch. We don't plug this as often as we should, but I'm wearing our Erlenmeyer Flask hat, and Melissa's wearing the Collegiate sweatshirt. Those you can find at chemforyourlife.com/store for a very, very nice price. And we've got a good merch partner that we like. So please show some love over there if you'd like to. And you can also help us by subscribing to your favorite podcast app, rating, writing, review on Apple Podcasts and Spotify, subscribing on YouTube, giving us a thumbs up or a comment over there. Those things help us to be found by people who are looking for chemistry content. If they're looking to understand the chemistry of their everyday life, why not find us? So those are some ways you can help as well if you'd like to.
That's right. And just to those people who are a part of our community and who are supporting the show, we like to give them a special thanks every single week. So we'd like to shout out Chris S., Hunter R., Katrina B., Lynn S., Scott B., Stephen B., Tim P., Vince W., Ash, Brian K., Chelsea M., Doreen V., Elizabeth P., Emily H., Heather R., John T., Jesse R., Latila, Rachel R., Autoclave, Avishai, Chelsea B., Sierra L., Cullen R., Emerson W., Erica B., Jacob T., Jeanette N., Julie S., Justine, Christina G., Suzanne P., and Venus R. Thank you all so much. Thank you all so much for everything you do to make this show happen. And if you'd like to learn more about today's episodes, you can check out our show notes or our website.
Or the description of the video.
I always forget that one.
That's okay. They'll figure it out.
Yeah, they probably will.
Yeah.
Yay chemistry.
Yay chemistry. Yay film.